Imagine this, it's almost midnight in a bustling city. A bank's data center is sensing millions of dollars in transactions between two locations. Suddenly, somewhere along the 100-kilometer route, a tiny component, an optical amplifier, fails. But within seconds, the data is automatically rerouted. Not a single transaction is dropped. Customers sleep peacefully, and the bank's operations continue without a hitch. That invisible miracle, that beam of light carrying our voices, videos, and financial data across vast distances, is the quiet heartbeat of modern telecommunications, fiber optic transmission. Yet, for many engineers, especially those coming from the world of radio frequency or IP networking, fiber is still a black box. Light goes in one end, and light comes out the other. But the magic in between feels, well, like magic. But to design, maintain, or troubleshoot a network that actually works, you can't rely on magic. You need to understand the fundamentals. So today, let's peel back the layers and illuminate the world of fiber optics. At its very core, fiber optic transmission is brilliantly simple. It has just light traveling through a very thin strand of glass. But of course, it's not just any light, and it's not just any glass. A fiber cable is made of three key parts. First, you have the core, which is the ultra-pure inner glass strand that the light actually travels through. Surrounding that is the cladding, another layer of glass that acts like a perfect mirror, constantly reflecting the light back into the core. And finally, you have the coating, which is a protective plastic layer that shields the delicate glass from damage. The whole system works because of a principle called total internal reflection. Think of it like shouting into a long, smooth metal pipe. Your voice bounces off the walls, staying trapped inside, allowing it to travel much farther. Fiber does the exact same thing, but with light instead of sound. This is why a fiber optic signal can travel hundreds of kilometers with incredibly low signal loss, something a traditional copper cable could never even dream of. And that brings us to the classic showdown: fiber versus copper. If you've ever worked with copper-based links like Ethernet or coaxial cables, you know their limitations. They carry electrical signals, which degrade quickly over distance and are highly susceptible to electromagnetic interference from things like power lines or machinery. Fiber, on the other hand, carries pulses of light. It's completely immune to that kind of interference, can span entire cities without needing a boost, and can carry mind-boggling amounts of data. To put it in perspective, a single strand of fiber, about the thickness of a human hair, can carry more information than a thick bundle of copper cables the size of your arm. That's why major telecom companies invest billions in massive fiber backbones that run under our streets, across the country, and even beneath the oceans. These cables are the arteries of the modern internet. Now, not all fiber is created equal. There are two main types you absolutely need to know. First is single-mode fiber, or SMF. This fiber has an incredibly tiny core, only about 9 micrometers in diameter. It's designed to carry a single, straight path of light, like a laser beam down a perfectly straight highway. This makes it ideal for long-distance transmission. We're talking intercity backbones and submarine cables that stretch for thousands of kilometers. The second type is multimode fiber, or MMF. As its name suggests, it has a much larger core, around 50 or 60.5 micrometers. This larger core allows multiple paths, or modes, of light to bounce around inside it simultaneously. Think of it less like a highway and more like a busy city street, with cars taking slightly different routes to get to the same destination. Because the light paths have different lengths, the signal can get a bit jumbled over distance. This is why multimode fiber is typically used for short-range applications, like inside a data center or across a university campus, usually for distances under 2 kilometers. So, how does your Netflix stream or your WhatsApp message actually get turned into light and sent down a piece of glass? It's a fascinating, high-speed journey. First, your data, which starts as one south and O south, is converted into electrical pulses. Then, a laser or an LED takes those electrical pulses and turns them into flashes of light. Light on is a 1, light off is a 0. This light then propagates down the fiber, bouncing off the cladding millions of times. After traveling 100 kilometers or so, the signal naturally gets a bit weaker. That's where optical amplifiers come in. Devices like erbium-doped fiber amplifiers, or EDFA boost the light signal directly, without ever needing to convert it back to electricity. Finally, at the destination, a photodiode detects the incoming light pulses, converts them back into electrical signals, and your device decodes those signals back into the data you can see and use. And all of this happens in the blink of an eye. To really master fiber, you need to grasp a few key concepts. The first is wavelength. Just like sunlight contains a rainbow of colors, the light used in fiber optics can have different colors, or wavelengths. This is where the magic of dense wavelength division multiplexing, or DWDM, comes in. DWDM allows us to send dozens of different wavelengths of light down a single fiber at the same time, without them interfering with each other. It's like having 80 separate, invisible highways packed into one tiny glass strand, each carrying its own massive stream of data. This is how we achieve capacities of terabits per second on a single fiber. Next, you need to understand the optical power budget. This is the crucial calculation every transmission engineer lives by. You start with the power of the light launched by the transmitter, and you subtract all the signal loss that happens along the way, loss from connectors, splices, and the natural attenuation of the fiber itself. What's left has to be strong enough for the receiver to clearly detect it. If your total loss exceeds your power budget, you'll get errors, or worse, no signal at all. Another critical concept is dispersion. As light pulses travel, they have a tendency to spread out and start overlapping with each other. In single-mode fiber, the main culprit is chromatic dispersion, where different wavelengths travel at slightly different speeds. In multi-mode fiber, you have modal dispersion, caused by the different path lengths we talked about earlier. To combat this, modern systems use clever techniques like dispersion compensation modules or advanced digital signal processing to unspread the signal and keep it sharp. Finally, a key metric for signal quality is the optical signal-to-noise ratio, or OSNR. Just like in any communication system, there's always some background noise. OSNR measures how much stronger your signal is compared to that noise. A higher OSNR means a cleaner signal and fewer errors, which is exactly what you want. Let me give you a real-world example. During a heavy rainy season, a construction crew accidentally cut a major fiber cable connecting to key business districts. Instantly, traffic worth millions of dollars per minute was at risk. But within milliseconds, the network's protection system automatically switched all the traffic to a redundant, physically separate fiber route. Most users didn't even notice a flicker. Their video calls continued, and their bank apps stayed online. That is the power of a well-designed, resilient fiber network. Now, fiber isn't perfect. It has its challenges. The biggest one is physical vulnerability. Fiber cuts from roadwork are incredibly common. The initial deployment cost is also high, and the fiber itself is sensitive. A sharp bend can cause light to leak out and degrade the signal. Maintenance requires skilled engineers and specialized tools like optical time domain reflectometers, or OTDers, to locate faults. But the industry is constantly evolving. We have coherent optics, which use advanced modulation techniques to pack even more data into each wavelength. We have software-defined networking, which allows for dynamic and intelligent control of the optical layer. And we have fiber to the home, bringing gigabit speeds directly to our doorsteps. So, what mindset should you have as a transmission engineer? You're not just a cable person, you are a systems thinker. You understand that the performance of the physical fiber layer impacts everything that runs on top of it, from IP traffic to cloud services. True mastery is being able to read an OTD or trace, calculate a power budget, and then explain to a manager, in simple terms, why the network is performing the way it is. Ultimately, fiber transmission isn't just about light, it's about trust. It's about ensuring that billions of bits of information, our communications, our entertainment, and our economy, reach their destination reliably and securely. It's the invisible backbone of our connected world. If you're a telecom engineer, mastering these fundamentals is no longer optional. It's your ticket to staying relevant in the age of 5G, the Internet of Things, and the cloud. The next time you see a marker on the street that says fiber optic cable do not cut, take a moment. Beneath your feet lies the nervous system of our digital civilization, pulsing with light and purpose. And it's your job to keep it alive. Thanks for watching. If you found this video helpful, please give it a thumbs up, and don't forget to subscribe for more content on telecom engineering. Let me know in the comments what fiber optic topic you'd like me to cover next.